morning, everybody. Thank you for joining us today. Today, I'd like to discuss secure communications for small microcontrollers. In the broader information technology world, there are 5 pillars to information assurance. So these are confidentiality, integrity, authentication, availability, and non-repudiation. So I'd like really to discuss how we can implement these on a small microcontroller system. So we need confidentiality to make sure any data that we're transferring can't be read by unauthorized individuals. When we receive the data, we need to be able to check its integrity, that it hasn't been manipulated by somebody during transmission. We also need to provide authentication to only allow valid users onto our system. And also our system has to be easily available as well. If we have a system that's too complicated to use, so that it's very difficult for non-technical users, then it's not really a practical system. And any data that's moving through that system, we have to provide non-repudiation. So if I send you a message, I can't later deny that I actually sent it. So we need to provide its integrity and origin. So we'll have a look at how we can implement all of these features within a small microcontroller system. Now, the main way that we can look at doing this is with a free open source library called Mbed TLS. This is a full cryptographic library that's provided free of charge by ARM. It was originally a commercial library, but ARM purchased the company, has now open sourced it so that it's free to use for commercial and non-commercial projects. This is available as a pack within the Kyle pack system, so that it will easily integrate into the MDK ARM toolchain. But you can also download it as source code from the Trusted Firmware website and use it with any other toolchain as well. So it's really just C code that we can include. It's very modular code, so that all the different algorithms that are included, you can just include the code that you're going to need for a particular algorithm. So it's rather than a large monolithic library, it's really been designed so that it will work well with a small resource-constrained microcontroller. Now, within the Mbed TLS library, we have a number of algorithms that we'll have a look through that are provided to give us our information assurance. So there are a range of ciphers, both symmetrical and asymmetrical ciphers, which we'll discuss in a bit. There are also cryptographic hashes, so that we can prove the integrity of our software. Message authentication codes that provide the integrity and origin of the software, of the data, sorry. Also within the Mbed TLS is a set of random number generators. So again, within the protocols and some of the algorithms, we need a lot of random data. So the absolute foundation of your cryptographic system very often comes down to having a very strong random number generators. These are very important parts of your design. And then sitting on top of the algorithms, there's a number of protocols that are provided, including the Transport Layer Security Protocol, so that we can establish secure communication between 2 nodes over the internet. So first of all, we have confidentiality. This is provided by ciphers, and there are 2 key families here: a symmetrical cipher, which we'll have a look at now, and an asymmetric public key cipher, which we'll come on to a little bit later. So within a symmetrical system, we have a cipher that will take some plain text, and in combination with a cipher key, will encrypt it to cipher text. And then using the same key, we can go backwards from the ciphertext to get back to the original plain text. Now, within this system, it's important to realize that the algorithm that we're using doesn't actually need to be secret. In fact, you should use publicly available ciphers that are widely known widely tested and widely used so that any weaknesses in them are discovered. The idea that we should keep our algorithm secret is completely wrong. The only thing that really needs to be secret in our system is the cipher key. And this is always within a small microcontroller one of the big problems, that we have to secure the key securely within the microcontroller. But ideally, we'll be using an algorithm where we're generating session keys. So the cipher key is only valid between the source and destination for the actual communication session that we're undergoing. And we'll see how that works in a little bit. So within Mbed TLS, there are a number of different ciphers provided. So the most widely used is AEAD, the Advanced Encryption Standard, and that's available with a number of different sized keys. So at the moment, probably the most widely used in a small micro is 128-bit key. This gives a good level of strength and also is quite fast to compute. So all of these symmetrical ciphers are fast enough to be used within a streaming system. So if we're looking at communication over the internet, then we can encrypt data within a TCP packet successfully with a block cipher. So in addition to AES is also the data encryption standard. So this is an older standard that really shouldn't be used for new designs, but really is there for legacy support. And there are also a range of other ciphers that are available and can be used with the transport layer security protocol as well. So AES itself is a block cipher. So it will take a block of data, and compute that with through a number of stages. So we'll have a set of substitution boxes that will we can use to substitute different bytes for different symbols. We then do a series of confusion rounds where we mix the data within the packet. So the strength of AES is built on a substitution cipher, but also by mixing the data in the packet through these two layers of confusion. We do this up to 14 times with round keys that are generated from the main input session key. So each round has a slightly different key, and we can still run through each of those rounds fast enough to be able to maintain a streaming data channel. However, there are problems. So although AES is a very strong cipher and there's no known way to currently break it, if we are streaming data, it's effectively a pseudo-random transform. So where we put in, for example, a block of white data, we'll always get out the same pattern the other side. So where we're sending, for example, a picture, it's possible that some amount of information within that encrypted data can bleed out to a crypto analyst. So here we can see that we've got sections of white data and black data in our picture, and it's possible to determine a sort of idea of what the image is if we just use straight encryption. So this is known as electronic codebook mode. What we need is to use a different or an additional method to get to fully pseudo-random looking data, as shown in the image on the far right. And the way that we would do this with a block cipher is through a method called chaining. So here we're taking the output of the algorithm and feeding that into or XORing that with the next block of data, and then feeding that through the cryptography algorithm. So this way we're chaining each packet of data, and we're providing an additional layer of encryption. So the XOR acts as a form of encryption. We're taking the randomized ciphertext and encrypting that with the next block of plain text. So this allows us to completely hide the image, but we need one additional block of data called the initialization vector. So this is a block of random data that's used to kick off the process with the first block of plain text. The initialization vector should be random data that's different for each communication session. Unlike the key that's used for the cipher, it doesn't need to be kept secret. So we can send it as plain text to the receiving station at the start of the communication session. But there are a number of different chaining schemes. But if you are streaming data, then you must use a chaining mode to fully secure your data. Again, if you're saving blocks of data, you also need to use a chaining mode if you start storing large amounts of data at rest as well. Next algorithm that we'll have in our cryptographic library is a hash algorithm. So here we can take a block of plain text, and this can be a few bytes of data up to the entire contents of War and Peace. So we feed blocks of those into the hashing algorithm, and then once we've fed all of the data through, it will give us a message digest. So this is a large number, which is effectively a cryptographically strong checksum of the input data. When we send the text to somebody, we can send a message digest alongside it, and then anybody receiving that data can recalculate the message digest using the hashing algorithm, and the two should match. So this allows us to prove the integrity of the software, that it hasn't been manipulated as the data has been transmitted. So there's a number of uses for hashes. So the obvious one, as we've discussed, is proving the integrity of the data. But it also acts as like a cipher. It's a pseudo-random transform as well. So by feeding data in, we can get almost randomized values out. So we can use it for key derivation. So we can take a stored key and we can feed that into a hash algorithm a number of times, and that will give us a unique number which we can use as a session key. Similarly, we can build random number generators that are built on hashing algorithms as well. Hashes are commonly used for password storage, so we can take the password and only store its hash, so that we can test against the hash when somebody gives us our password. In code, it's also possible to use it to protect critical functions. So for example, we can hash the stack space, run a function, and when we return, we can check that the stack hasn't been manipulated as well to protect against software attacks. And there's also a primitive form of blockchain called a hash chain, which we can use to store data or generate one-time passwords as well. So there are a whole range of hash functions. The original one was the message digest family. This is now pretty much obsolete, as hackers have found ways to compromise this hash. So there's a new family of hashes called the secure hashing algorithms. These are developed by the NSA in the States, and are probably the most widely used now on the internet. Although you'll still see the message digest around, it's mainly there to prove the integrity of a download that hasn't been corrupted as you've downloaded something. So for new designs, we shouldn't use any of the message digest algorithms. Also now, more recently, the SHA-1 algorithm has been broken, so we can, that's been compromised. So the minimum that you should use is SHA-2. And this should be okay for the foreseeable future. So currently, the internet is moving to signing X.509 certificates with SHA-2. Now, alongside hashes, we also have message authentication algorithms. So a MAC is really a hash with a password. So when we generate the hash of our data, we also combine it with an input password so that when somebody receives that data, they can recreate the message authentication code using the data and the password. If that's correct, they know that the integrity of the data is okay, and that whoever sent the message had the MAC password. So it's also a form of authentication. So typically, when we're streaming data, we'll encrypt the data, but we'll also have a MAC at the end of the data so that we can prove the both the origin and the integrity of the data as well. Now, if we are streaming data, that means that we're using two algorithms, the MAC and the cipher. So there is a new standard called authenticated encryption with associated data. This provides a single set of APIs and works with a single session key to both encrypt data and generate a MAC as well. So this allows us a very efficient way to generate frames of data which are both encrypted and have a message MAC, a checksum effectively at the end. The associated data is actually a block of plain text that's included in the data that's calculated by the MAC. So in a TCP frame, we'd have the header, which would be the plain text, followed by the frame data, which is encrypted. And on the end, we'd have a MAC, which includes both the header and the encrypted frame. Then there's a matching API that can be used to decode that data on the fly as we receive it. So AEAD is a very efficient way to generate streaming frames of data where the encrypted data is effectively locked to the message packet and can't be replayed or reused elsewhere. Now, underpinning many of these algorithms, as I mentioned, are random number generators. So generally, a lot of newer microcontrollers that are designed as IoT devices will have a true random number generator built into them. So these give us a good source of random data, but they're often quite slow. So this random data is often stretched into larger amounts of random data using an algorithm called a deterministic random bit generator. So this will take our true random data and then expand that to larger amounts of pseudo-random data. Very often, though, we'll store some of our true random data in an intermediate buffer called an entropy pool, and this is then used to feed our deterministic random bit generator. So the random number generator is quite a small system in its own right. It's very important to the strength of our overall cryptographic system. So one of the things that you really do need to try when you're first building a system is proving the strength of your random number generator. And there are a number of different ways of doing this and statistical test suites that are available. But early on in your design, you should look at taking some measures to prove that your random number generator is actually a cryptographically strong random number generator. Or you'll have a weak system that is liable to be hacked. Now, in terms of secure communication, we really want to use symmetrical ciphers because they're very fast and efficient. But we have the problem that the key has to be distributed between all the stations that need to communicate. And trying to distribute that key over an insecure channel is a difficult problem. Our key ideally has to be a session key, so it has to be a different key for each session that we undertake. And any permanent keys will have a limited lifetime, so they have to be rotated. And if a permanent key is compromised, we also have to have a means of replacing it as well. So again, key management within our system is something you need to think out early in the project. But in terms of the secure communication, agreeing a session key is the main process, or the main point of the transport layer security algorithm. We have an initial key agreement session where we set up our symmetrical key. In order to do this, we need to both have our asymmetrical encryption, so public key encryption, and we then also need a means of distributing public keys securely over the internet. So this is a much larger public key infrastructure that we have to understand to build our secure communication. So at the heart of this is our asymmetrical algorithms. So this is public and private key communication. First of all, unlike a streaming algorithm, we actually have to do some computational work to create a public-private key pair. This can be done on the microcontroller, but it's quite time consuming. So generally it will be done on a larger computer, and then our private key is stored in the microcontroller. And as its name implies, the public key can be public information and can be given to any other third party. Once we've generated the keys and placed them either into the micro and distributed them to our users, somebody who wants to send a message can encrypt the data with the public key and then send it to the receiving station. There, the private key is used to decrypt the data, and then we can act on it. Now, this looks like, on the face of it, a solution to all of our problems. However, public key or asymmetric cryptography is quite slow, so we only can really use it to encrypt relatively small amounts of data. So very often the public key is used to encrypt or to wrap the session key, which is then sent to the receiving station, which will then decrypt it and use that session key for symmetrical key encryption. However, one of the other issues with asymmetrical algorithms is that they use very large numbers, 2,000-3,000 bits or greater. So these big numbers require a special library and special techniques to use them. And these are called multi-precision integers, so that we have a library that can handle these something like 2048-bit, 3,000-bit and greater integer numbers. So this is also part of our cryptographic library as well. So within our asymmetrical ciphers, we have probably the two most widely used algorithms are the RSA algorithm, which is a crypto system, and secondly is the Diffie-Hellman algorithm, which is a key agreement algorithm. So that creates a shared secret between two different stations. There's also elliptic curve cryptography. We'll come on to this, but we can have an elliptic curve version of Diffie-Hellman as well. Alongside cryptography, or being able to encrypt data, we can also use public key cryptography to sign data as well. And this allows us to prove the authentication or where the data originated from. So we can sign a message with a private key so that anybody receiving that can validate it with the public key, and there's only one person that could have generated that message. So we can use asymmetric ciphers for encrypting small amounts of data, and also, very importantly, being able to digitally sign data as well. We'll see how that process works in a tick. So RSA, as mentioned, is an encryption system. Again, all of these things are quite slow, and it's really used to wrap a session key that can be used with a symmetrical algorithm such as AES. However, it does suffer from some problems in that a school book or plain encryption is malleable, in that this means that an attacker can't read the data, but they are able to manipulate the message so they can change the data inside, and when it's decrypted, you can't tell that it's been attacked. So to use RSA properly, we need to have a padding scheme that puts patterns inside the message so that we can detect that if anybody has attacked our message. So RSA on its own is not a practical encryption system. You must use a padding scheme with it or you're vulnerable to attack. Diffie-Hellman is used, but probably RSA is about 90 to 95% of the systems in practice. So Diffie-Hellman is probably, I say, much smaller, far less used in practical systems. But it's as I say, it's not an encryption system, it's a key agreement. We can exchange data, and with a combination of our public and private keys, we can come to a shared secret between two different stations that need to communicate, and then this can become the basis for our session key. However, with Diffie-Hellman, you can't sign messages, so we need a separate signing algorithm. Yeah, and that algorithm, typically we can either use RSA for authentication or a separate algorithm, which is the digital signing algorithm. So this will validate the data and authenticates the user who the sender was. So with RSA, the way that we can calculate a signature is in our plain text, we can calculate the hash. We can then encrypt that hash with our RSA private key, and this gives us a digital signature. So we can send that alongside the data so that the receiving station with the public key can decrypt the signature to get the original hash. We can recreate the hash over the plain text, and that should now match the signature hash. If the two are matched, then the data hasn't been manipulated, and it has been signed by the private key of the sender. So that signature now proves the authentication, or authenticates the text, and also proves its integrity as well. Within the Mbed TLS library, there's also a set of algorithms that use elliptic curve cryptography. So as I mentioned, Diffie-Hellman, and there's also an elliptic curve digital signing algorithm as well. So elliptic curve cryptography effectively replaces the standard number line with an elliptic curve. So we're now doing maths on our elliptic curve. So this provides a stronger level of encryption so that we can use smaller sized keys to give us the same strength of encryption as RSA. So for a small microcontroller, elliptic curve cryptography is very useful because, again, we need to do less computing and therefore using less energy. So again, there are a number of microcontrollers now that have built-in hardware accelerators to do elliptic curve cryptography for this very reason. So again, when you're designing a system, as I say, a lot of cloud services use RSA, but increasingly we're seeing the adoption of elliptic curve for, again, power and computing resources. So again, here we can see the size, the equivalent strength of the keys for 100. So for example, to match a 128-bit key within AES, an elliptic curve key needs to be 256 bits long, whereas RSA is over 3,000 bits. So again, we can make some big savings by using elliptic curve cryptography. And when we actually come to establish a secure channel, on the face of it, we need, for example, the station that wants to communicate to, for example, Alice, to request a public key from Bob. He will send his public key. Then Alice can encrypt a session key within that, send that back to Bob, and now we have the same symmetrical encryption key at both ends, and we can start to stream data. Now that's quite a naive channel, because we can have malicious actors that can intercept that communication and substitute their own keys. So while Alice thinks she's talking to Bob, we can have Mallory in the middle, who's able to receive all of Alice's messages, decrypt them, re-encrypt them with Bob's key, and send them on. So we can have a malicious actor that acts as a man in the middle, and able to receive and read all of our communications. So we need this public key infrastructure so that we can securely transfer our public keys reliably between stations. One of the main ways to do this is to have a trusted third party called a certificate authority. We give all of our credentials to the certificate authority, and they will generate a X.509 certificate, which is signed by their private key. And they'll return us our credentials in the form of a certificate with their signature on the bottom. In addition, the certificate authority also publishes their certificate authority certificate, which contains their public key, which we can use to validate the certificate. So everybody has the CA cert, and then when you receive a certificate, you can recalculate the signature using the public key within the CA certificate. This way we can exchange certificates and prove their integrity by our root of trust, which is the CA certificate. So within an X.509 certificate, we'll have our own public key and then a signature of the certificate authority at the bottom. And then within the subject area, we'll have all of our details plus a field called the common name. Now, the format of the data that goes into the common name field isn't rigidly defined, but it's usually the URL of the website that's associated with the certificate. So in there'll be google.com or the name of our server. So this means that the public key is now tied to that website, and all of that is validated by the signature of the CA. So when we receive the certificate, we can extract the public key that's associated with a specific website. And we're also validated that by our root of trust, which is the signature of the CA. So this prevents a man in the middle substituting data because we can always trace it back to the common name and the public key associated with it. Now, in an IoT system, that common name is usually the URL of the server that's being at the center of the system. You shouldn't use an IP address in there, so it should be a proper URL. So when you're designing a system, if you're connecting to a public IoT cloud system, that will provide you with a certificate for your device and also their own CA certificate. However, if you're designing your own system, it's possible to create your own server and then generate and manage your own CA certificate and issue certificates to all of the nodes in your system. So this means that you can create a sort of a walled garden where only nodes that you want are allowed to connect. So when a client needs to connect to a server, we'll use the transport layer security protocol. So this is mainly based around an initial handshake where we are transferring our certificates, a number of bits of random data that will become the session key, and also establishing the credentials of both the client and the server. So normally when our browser connects to a web server, we are receiving the server certificate and validating it. With an IoT system, we can also place a certificate within the client that's sent up to the server. So the client is validating the server, and the server is also validating the client. So this basically creates us what is a higher level of security than when you are connecting to a secure website with your web browser. It also allows us to remove clients from the system by banning their certificates as well. So this gives us quite a higher degree of control over our overall system. Within the Mbed TLS library, there's a lot of low-level functions that allow you to use all the cryptographic primitives. But there are a number of abstraction layers as well, so that we can start a TLS session with a very high-level set of function calls, and those will call abstraction layers for both ciphers, MACs, and hashes as well. So again, we can install suites of ciphers and MACs and switch between different ciphers, MACs and hashes as our system is required. Once we've established communication, probably one of the most dominant form of protocols used to transfer data within an IoT system is message queued telemetry transport. This is a publish and subscribe system. It's a very low footprint system. It's quite easy to use. It's also royalty free and an open standard as well. Typically, our small IoT nodes are connecting to a broker, which is the server, and they will publish a message topic. And again, this can be made up on the fly. So it'll be a topic and data. This is created within an internal database in the broker. And whenever we update the topic, it will be reflected out to any other node that has subscribed on the system. So this can be another IoT node, or it can be a piece of PC software. So this gives us a nice lightweight way of reflecting data from our IoT nodes to many different systems within our overall system. In terms of the embedded client, there is an open source client called Faho. So this gives us a set of lightweight functions that we can put into our application to create MQTT packets and send those up to our cloud server. These are available as software packs, which are free to use within the MDK. So we have a Faho pack. We have the packetizing system. There's also support for Wi-Fi modules. So there's a new CMSIS Wi-Fi standard so that we can easily hook on to supported Wi-Fi modules and create secure communication sessions. As I mentioned before, there's also the Mbed TLS cryptographic library. So again, that can be added and integrated directly into this system as well. So creating a simple IoT node with secure communication is really a matter of selecting the options that we want to use within the runtime environment manager within the Kyle tool, filling in the certificates and configuration options, and then we have some very high level functions to call to start our system working. That's almost the first half of developing a secure application. We can get secure communications, but then we also have to make our device secure against network software attack. This can be managed with the newer ARM V8 based Cortex microcontrollers. These include a security peripheral called Trust Zone that allows us to partition our device so that we can create a security enclave, and within that we can put a set of software called the trusted firmware that provides our cryptographic functions to our main application software. So this method creates a layered defense against software hackers, and this will be the subject of our next webinar on the 8th of June. All of this is I've just written down and released in a new book which was published about a week ago, and this goes through the both the secure communications and the ARM platform security architecture in excruciating detail. So I hope you'll be able to join us next time. We will have a look through the ARM platform security architecture and also the trusted firmware, plus the sort of support that's provided by some of the newer microcontrollers based on the Cortex-M33 and even the newer Cortex-M55. So thank you very much for joining us today. I hope that's been interesting. If you have any questions, please let me know and I'll come back to you by email.